This is the first class on theory of sets. Although it is only from recent times that the concept of a set is being extensively used in the study of mathematics. The idea of a set is one of the earliest concepts of many. The theory of set, as developed by George Cantor, is being used in almost all branches of mathematics nowadays. As in the case of the concepts of geometrical point, line, and a plane, a rigid definition is not possible for a set also. It is the intuitive conception of a collection of things, real or conceptual. The set is a well-defined collection of objects which are called members of the set or elements of the set. Objects belonging to the set or object belonging to the set must be well distinguished. By well defined, we mean that it must be possible to tell beyond doubt whether or not a given object belongs to the collection that we are considering. For example, peoples of your class is a set while all good tennis player of your school being not well defined. Hence is not a set. Why? Because it is difficult to say who is good and who is not. So set is not only collection of object, it should be well defined. So well defined means it must be possible to tell beyond doubt whether or not a given object belongs to the collection that we are considering. In this example, pupils of your class, we easily say that which object belonging to in that class or not. But all good tennis players of your school, it is not possible to say which object belonging to this class or not. So this is not a set, all good tennis players of your school, but pupils of your class is a set. So this is the definition of set. So some other example of sets are, suppose these are the some others example, a set of integers prescribed conditions. For example, a collection of integers, positive integers less than equal to 10. So prescribed condition is less than equal to 10. Next, another example. A set of books in the library another example, a set of rules, set of the rules for the football game a set of rivers in India a set of living scientists of the world, etc. These are all example of sets. If the set capital A, we generally denoted by capital letter, set by capital letter. If the set capital A consists of the elements one, two, three, 4, then we express the set in the tabulation or tabular form A within braces 1, 2, 3, 4. So this is the tabular or tabulation form. That is by writing the elements separated by commas and enclosed in braces. So in tabulation or tabular form, we write the elements which is separated by commas and enclosed in braces. a set of elements which are vowel A, I, O, U is thus A, E, I, O, U. A set is expressed in the set builder form, also by displaying a typical element and by starting the properties this is not starting, this is stating. A set is expressed in the set builder form also by displaying a typical element and by stating the properties which the elements of the set must satisfy. So we see that we represent set two ways. One is tabular form and another is set builder form. In tabular form, we write the elements which are separated by commas and enclosed in braces, and in set builder form we display a typical element and by stating the properties which the elements of the set must satisfy. Thus, the symbol capital A, we read it as collection of X, P within bracket X, this is the property. For example, or some book, instead of this perpendicular line, we write it double dot, we read it as such that X, collection of X such that, then we write the property. States that A is a set of elements X which satisfy the condition Px or property Px semicolon. The symbol is read it as such that Px here specifies a property satisfied by all the elements X of the set. This is the example. Suppose we represent set A in tabular form. This is the collection of these elements. So we write it in set builder form. Then it should be collection of X. What is the property of X? X is a positive integer less than 40. Now, if your set A, suppose this is your set, then you write it as collection of X such that X is a positive odd integer less than 40. Similarly, this is collection of X such that X is equal to 2n, n being a natural number. Or you can say collection of X such that X is even number. Now we consider another example. Capital X, collection of 1, 8, 27, 64. Then it is collection of X such that X is equal to n cube, n being a positive integer. Another example, this is collection of x is equal to 5n, n being 0 or an integer positive or negative. So these are the example of set Tabular form. Now a set having no element is defined as the null set or empty set. An empty set is generally denoted by the symbol phi or this. The following are examples of null set. Set of people who can work more than 24 hours a day. So, no, it is impossible to work more than 24 hours a day, because in a day we know only 24 hours. So, it is null set. Another example, set of triangles having two centroids. Which is again a null set, because this is impossible. Another example, collection of extras that x is a real number satisfying x square plus 3 equal to 0, which is again impossible. When x is real, then x square plus 3 equal to 0 is not possible. So these are the example of null set. A set having only one element, 0, having one element, a set having one element is called a unit set or singleton set. For example, collection of x, T is a set, which is a collection of x such that x plus 2 equal to 0. This contains only one element, that is minus 2. So this is the example of singleton set. A set is finite if it be empty or contains a finite number of elements. Otherwise, a set is infinite. So this is a finite set, example of a finite set 1, 2, 3, 4, because it contains only 4 elements. Or we can write it in another way, collection of x such that x is positive integer less than equal to 4. So, or x is a natural number, rather than you write it natural number less than equal to 4. So this is the example of finite set, and a set of natural number generally denoted by capital N, which is, this is a example of infinite set, and this is example of finite set. The number of elements of a finite set capital A is called the order or cardinal number of the set capital A, and is symbolically denoted by n within bracket a. Thus, if the set capital A be that of the English alphabet, then NA should be 26. Since it contains 26 elements in it. Again, if A is a set of a vowel A, I, O, U, then NA should be 5. So there are, suppose set A containing only 2 elements, say 1 and 2, then NA should be 2, and so on. An element does not occur more than once in a set. For example, if we have the numbers 0, 1, 1, 3, 4, 4, 0, 3, 1, then the set corresponding to this numbers is 0. Since 1 repeated thrice, so it contains only 1, 3 and 4. So the corresponding set is this. Similarly, then the corresponding set is this. It should be remembered that listing the element in different orders does not change the set. That is, set 1, 2, 3, 4 and 4, 3, 1, 2 are the same. So you should remember this point. Listing the elements in different order, listing the elements in different orders does not change the set. So the one point is an element does not occur more than once in a set, and another point is listing the elements in different order does not change the set. You should keep these 2 points in your mind. The following symbols are used to denote some well-defined set. This is denote the set of all natural numbers this is denote the set of all integers. This is the set of all rational numbers. This is set of all real numbers. This is set of all complex numbers. This is set of all positive numbers. This is a set of all positive even integers. Z plus, Q plus, R plus denote the corresponding sets of positive quantities only. That means Z plus means set of all positive integers, Q plus means set of all positive rational numbers, R plus means set of all positive real numbers. So I want to stop here today. In my next class I will discuss subset. Till then, please stay with us. Thank you.